All right, folks. In this video, we'll be looking at how complex functions interact with as a mapping. So in order to get into this concept, we're going to be looking at what is called the image of a function. Okay. The image of a function under of a function, I'll say f of z, right? Z is a complex number. So for I guess the downside for complex functions is, well, we can't draw a complex function entirely, right? We would need 4 dimensions to do this. Unfortunately, we live in a 3-dimensional setting, so bummer. However, the next best thing is to look at images of one subset in the complex plane into another subset of the complex plane. Okay, and here's the idea of what an image of a set is. So if I take some subset in the complex plane, we'll call it S, right? The goal here is we want to look at what this set will look like if I project that function, a complex function f, and what that will look like is an entirely different set in another complex plane. So we'll call this S prime. Okay. So, so for every point that's in S, we'll call this Z. We want to look what this will map. So what Z will get mapped to inside this set. We'll call it W, right? So UV and then X and then Y. So we're going to take one set in the complex plane. We'll call this the Z plane. And we want to look at what functions, what outputs will look like in the S set in the W plane, right? In the W plane. So S prime would be the following definition. So if W is equal to f of z and describes a complex mapping okay, and S is a set of points in the, I'll say the XY plane, or they call it the Z plane. We'd call the image of points in S under F. And this is denoted as S prime. S prime. S is the set in the XY plane, and S prime would be the set in the UV plane, or they call this the W plane, right? UV plane is also what it's called. Okay, so that's the basic idea of the images of a set. Okay, so for an example, let's look at this example here. So we want to find the image of S S prime under the given complex mapping W equals f of z, okay? So if I have this function, f of z equals to I times z, and then S, this set in the xy plane, is the horizontal line at y equals 3, okay? So I want you to work on this example here, just for a few minutes, and see what you come up with. Okay, so I assumed you worked at this example here. So let's actually look at the image of this given set. So if I were to label the XY plane, okay, this is the XY plane. So we're going to look at the images of the set under the line y equals 3. So for sake of demonstration, let's look at if y equals 3 would be this line here, right? Going on indefinitely that way, right? So this is the xy plane. Okay, so it's at y equals 3. So a point that's on this line, right? Z, well, it's given as this complex number. X is varied, but the y coordinate is 3, so it's x plus 3I, right? So any point on that line is given as x plus 3I, right? So we can explore this just a little bit further in our function, f of z equals I times z, right here. So IZ is right here, and so a particular complex number on this line, right, x plus 3I, but that equals to I times x plus 3 times I, right? X plus 3 times I. If I distribute the I across the quantity x plus 3I, I'll get I times x minus 3. Okay, so in terms of the real and imaginary components, the function is equals to minus 3 plus x times I. Now, this is interesting. This will encapsulate the image of the line y equals 3, right? Y equals 3. So in the UV plane, all right, so this is we'll call this the W plane. So the image, so if this is S prime now will be, so S prime will be the line, so x equals 3. Okay. I'm sorry, it's the line x equals negative 3. Excuse me. So x equals negative 3. So if I just readjust this a little bit more to look like this, and then x equals negative 3 is over here. So the image S prime will be a line x equals negative 3, right? So that's the line x equals negative 3. Okay. So that's how you find the image of that set. Okay. How about this other example? This one here. Okay. So if I have W equals Z squared, and S is the vertical line x equals 1, excuse me. Vertical line x equals 1. Try working on this one. So you want to come up with the image under this function, W equals Z squared. Okay, so I'm assuming that you worked on this for a bit. So let's actually look at what the image would look like in this case. So let's draw out the XY plane. So the XY plane, okay. So the set S will be a vertical line x equals 1, right? X equals 1. And then points that are on this line, if I just pick a random point, well, it's going to be 1 plus y times I. Y is varied, okay? So the x coordinate is always 1, okay? So we already know that f of z is z squared, okay? And so to break that down into its real and imaginary components, x plus iy, okay? So this equals to x plus iy squared, and that would be x squared plus 2 xy times I minus y squared, right? And so the real component is x squared minus y squared plus 2xy times I. So, okay, this is interesting. So in the UV plane, the image so the function z squared, I'll start with that. So u is equal to x squared minus y squared. The v function is 2xy, right? So for any point in S, right, we had at any point in S, we had z equals 1 plus y times I. So x is 1 and y is varied. So that means under the point z equals 1 plus y times I, u is equal to 1 minus y squared. And then v is equal to 2y, okay? Hopefully this makes sense. And I'm going to redraw this graph here just a little bit so you can emphasize what's happening here with this image. So this is the W plane, right? So this is the W plane. U and then V is here, okay? So since X is 1, we can actually observe what these points will generate, okay? Well, if we solve for y in this bottom equation, we have that y is equal to v over 2, right? And so we can express u in terms of v. So u is equal to 1 minus v over 2 squared, but that is equal to 1 minus v squared over 4. So this would equal to u. And what that looks like is a parabola, right? But it's opening towards the u direction, okay? So if v is 0, if v is 0, u is 1. So right here, we're going to start off. Actually, let me do another color. So this is the S prime. So when v is 0, u is 1. So we'll have 1, 0. And what's interesting is that when v is 2, when v is 2, y, okay, so when v is 2, u is 0. And when v is negative 2, u is 0. So so this is 0, 2, and then 0 minus 2. And what it turns out is it's going to be a parabola opening towards the left. Okay. So this is S prime, as opposed to this being the set S, not S prime. Okay. So that's just another example of finding the image of a set. Okay, so hopefully that made sense. So what I'm going to go over next is different parametric curves of complex numbers. So, oops, there we go. Can I work this thing? Uh-oh. What's happening? Can I scroll down? Okay, so okay, I'll just work with it. So the next thing I want to talk about is parametric curves in the complex plane. And this refers to parametric curves in Calc 3, right? So here's the parametric equations of a line in the complex plane. Z of t is equal to z naught 1 minus t plus z1 times t. Times t. So these are functions that's varied by parameter t, right? T being like a unit of time, for example. So this is a line. Here is a line segment. A line segment. It's the exact same equation, but the limits for t will change. So 1 minus t plus z1 times t. T is in between 0 and 1. Okay. So when t is 0, we're starting at z naught, and when t is 1, we're at z1. Okay. Array. That's when you're starting off at 0 and you're going towards infinity in one direction, right? So this is z naught times 1 minus t, excuse me. Z naught times 1 minus t plus z1 times t. Let's say 0 is t is bigger than or equal to 0, but yeah, so it's extending out towards positive infinity, right? And then the Gradal circle, right? This is the parametric curve for a circle. Z of t is equal to z naught, that's the center, plus r times e to the it. Okay. And then 0, t is in between 0 and 2 pi, right? You can also write out as z naught plus r times cosine t plus I times sine t. Cosine t plus I times sine t, right? Okay. So those are different parametric curves in the complex plane that you'll see here. There's also the definition of finding an image of a parametric curve. These are really easy to work with. Okay. The image of a parametric curve under the complex plane, right? So this is how you figure out the image of a parametric curve, right? W equals f of z of t, right? Where t is in between a and b, right? Okay. So here's an example. Describe the curve in S in words and find the parameterization of the curve in S and describe this curve in words. Okay, so how about this one? So let's do part A here. Part A here. So z of t is equal to 2 times 1 minus t plus I times t. And we have our function equal to f of z equals to 3z. So I want you to figure out the image of this parametric curve. Okay, so pause the video and I want you to work on this example. Okay, so we want to describe the curve that's given by z of t, right? 2 times 1 minus t plus it, right? So this is, this here is a line segment from the point 2, 0. I should say the complex numbers z naught equals 2 plus 0 and z1 is equal to I. So this image in S, let me actually do it yellow here. So this image in S, right, would be a line segment going from 2, 0 on up to 0, 1, right? Going in this direction. Okay. All right. And so this is the z plane. Okay. So what we want to do is figure out the image, right? So we want to figure out, so this is S, right? What we want to do is figure out S prime. We want to figure out S prime, the image of S, right? Okay, so by that, we just plug in our parametric curve into our function, right? Our function was 3z, right? And so this equals to 3 times the parametric curve that was given, right? So in this case, it's 2 times 1 minus t plus I times t. I times t, right? And then t is still in between 0 and 1, right? The limits of your parameter, the limits of your parameter t does not change, right? So this would equal to 6 times 1 minus t, 1 minus t plus 3 times it. Now, what this curve describes is also another line segment. This is another line segment, but it's scaled by 3. Okay, so in other words, right here is the W plane. Right, so here's U and I guess V, right? So the new U point, this will be at 6, 0. 6, 0, right? So the new Z naught, I'll say Z naught prime, this equals to 6 plus 0I, right? Z1 prime, its image is equal to 0 plus 3I, right? So we're going to have another point here, 0, 3. Okay. And so this would be the image of S prime. It's just the same line, but it's scaled up by 3. Okay, so S prime would be there. Okay, so here's S, right? S is here, and then S prime would be here, right? So hopefully that made sense. How about this example? How about this one? So we'll have z of t equals to 1 plus 2 times e to the it. And t is in between 0 and 2 pi. And then f of z is equal to z plus 1 minus I, right? Z plus 1 minus I. Pause the video and I want you to work on this example and see what you come up with. Okay, now you've worked on this example. Let's look at what the parametric curve z of t will look like. Well, it's a circle, right? So on the z plane, we will look at a circle of radius 2, the radius is 2, and the center is at 1 plus 0 I. So the set S would be, so at this point, and we'll have a radius 2. So one of them is at 3, 0. The other is at minus 1, 0. Let me scale this just a bit more. And then let me erase this. Oops. So this will be the circle of radius 2, right? This is how we define z of t, okay? So if we notice f of z, z plus 1 minus I, so this would equal to 1 plus, okay, so we know that f of z is z plus 1 minus I, then f of z of t, well, this would equal to, so 1 plus 2e to the it plus 1 minus I, right? Plus 1 should be a minus I there, okay? And so this would equal to, so, okay, we'll have 2 minus I plus 2 times e to the it, okay? So this is another circle, So let me erase that. So this would be the image of S prime. So this is another circle. The center is at 2 minus I, and the radius is still 2. The radius is 2. Okay. All right. So we transform to one circle into another circle. So 2 minus 1. So 2 minus 1 will be the center. And radius 2. So this would be 2. Oh, oops. Let's say 4 here, and then 0 is there. Okay, so we'll have this, and then it's a circle, it's not an ellipse, so drawing is not to scale here. So 2, 1, oops. And this would be your circle. Oh, oops. Yeah, okay. Hold on, let me backtrack. That's my center. And so I should be going down. And then one is here. Okay, one is here. And then two would be here. Okay. Let me clean this up a little bit. And then this point will be down here. So this is the circle S prime, and that's the center. 2 minus 1. Okay. So this example will take an image of a circle and it will map to another circle. Okay. So hopefully you made sense with those examples and those definitions. And I want you to work on these problems for comprehension. So let me write out the page numbers. So so this is page 60. 2, 4, 8, 12, 16, 18, 21, and then 23. Okay. As always, please let me know if you have questions. But other than that, I will see you all in the next video. Great learning.